Hello everyone, good morning. Let us start. Continuity of function for your board examinations as well as the concept we learn here is required for all kinds of competitive exam. Let me discuss one by one. Today's class basically I am going to discuss the concept which is given in your textbook and will be solving some problems on continuity. First you try to understand the concept of continuity. In this chapter of continuity, limit plays a very important role. Okay? Role of limit is very important here. Why have I told so? Because just after one step of limit, the concept of continuity will arise. I can state this manner. You have seen that limit x tending to a. I hope all of you are good at calculation of limit, although I am going to remind you some important limits. Then you will be starting the concept for limit x tending to a fx exists if left hand limit, that is limit x tending to a minus fx is equal to limit x tending to a plus fx. Okay, this is the condition for existence of limit at a point. But limit will not ensure that continuity of a function. Everything you are discussing, say on the graph of function. So when there is limit existing at a point, then we can say that the just before the point or after the point just before or just after the point, the value of the limiting value of the function exists. This part you can consider this point say corresponding to a plus and this point corresponding to the point a minus. So these two are equal. At a plus, if you calculate the value of the function, at a minus if you calculate the value of function, they are both equal. I mean their length will be equal. This length will be equal to this one. But can we draw the graph in between 2 points a plus and a minus? This we can draw if we can say that the graph of function can be drawn through that point. If we say that the functional value also at that point exists, then it will be continuous at x equal to a. So continuity of a function means continuity of a function implies continuity of the graph of the function. Okay, continuity of a function implies the continuity of graph of function. So we can define continuity of a function at a point like this. A function y equal to fx, a function y equal to fx is continuous, is said to be continuous, in an interval if the graph of the function can be drawn in the interval without any break or without raising without lifting your pen or pencil. Okay, whatever you are using for draw the graph of function, if you can plot the graph of function without lifting the pen or pencil, then the function is said to be continuous. Okay, so if I say that the function is continuous in this interval between 2 points a0 and b0, then the graph of function continuous, and analytically the functional value equals with the limiting value at every point, isn't it? So when you say that it is continuous in the interval AB, this condition of continuity is obeyed everywhere at a point in between, that is left hand limit equal to right hand limit equal to functional value. Okay, then we will say that function is continuous. So I hope you have understood the meaning of continuity at a point and continuity in a interval. See, the meaning without lifting the pen or pencil you can draw the graph of function will not bring marks for you in your board examination, whatever board you are appearing, or entrance examination. But this is a very good definition to understand. The graph of the function is continuous, then the function is said to be continuous. Analytically, left hand limit, right hand limit and functional value at the point must be equal. All three must be equal. Today we are going to do continuity at a point, continuity in an interval. Then we will be discussing continuity of elementary functions, continuity of composite functions, algebra of continuous functions. So this class is on understanding continuity of a function. If you find JEE sums, JEE advanced sums today's class, you won't get it. But you should have a better concept of continuity with me today. Okay. So let us work on it first, continuity at a point, and then we will go for continuity in a interval. Suppose a function is stated this manner, not taking from any particular book, I am just writing a problem that fx equal to 3 minus x square, x is less than 1, this is equal to 2 for x equal to 1, and this is equal to 4x minus x square for x greater than 1. Is this function continuous at x equal to 1? I am talking about the point first. Interval will come later. You understand continuity at a point. So what you are going to do here? Check continuity at x equal to 1. Alright. You are going to check continuity at x equal to 1. So start answering this. For continuity, we will be finding the left hand limit, the right hand limit and the functional value. So let us find LHL at x equal to 1. It is limit x tending to 1 minus fx. This is nothing but limit x tending to 1 minus, you will be taking this part because it is less than 1. This concept of limit you got earlier, so substitute there. This part of the function 3 minus x square, the value is 3 minus 1 square this is equal to 2. The right hand limit. What is the right hand limit? Let us calculate here. Left hand limit part you have understood. Let us do a right hand limit. A right hand limit at x equal to 1 is limit x tending to 1 plus fx. This is limit x tending to 1 greater than 1 is this part. 4x minus x square, it is 4 into 1 minus 1 square. This is equal to 3. Unfortunately, this is not matching with the left hand limit. If it matches, then also you need to calculate the functional value. Functional value is quite obvious that f1 is equal to 2. Here you see x equal to 1. Add x equal to 1, fx is 2. So f1 is 2. So what will be your conclusion? Just by these two steps only you can say that the function is not continuous at x equal to 1. Clear? Understood? Now let us take a problem of this kind. If the function fx equal to this is continuous at x equal to 1, then find the values of a and b. So for this problem, what we are going to do, we will be using this set continuous at x equal to 1. So this is a problem on continuity at a point. So we will write this information first. For continuity at x equal to 1, LHL equal to RHL equal to f1. Agree? Left hand limit, right hand limit, functional value they are equal. Left hand limit, how have we written? Limit x tending to 1 minus fx equal to limit x tending to 1 plus fx is equal to f1. So let us write this. Tending to, 1 minus is this part, 5ax minus 2b. So by using the concept of limit, if you are putting the value, you are not carrying it, then 1 minus you need not write again, because you are putting the value here, and limit x tending to 1, this is 3ax plus b, and f1 is 11. Okay, so this is the condition here. So this implies 5a into 1 minus 2b, 3a into 1 plus b equal to 11. Therefore 5a minus 2b equal to 11, number 1. 2a plus b also 11, this is number 2. Clear? So what you are going to do there, you are going to get the value of a and b. That can be found easily. Just to use the condition of continuity, we got two equations. Let us solve. Multiply, with 1 you add 2, after multiplying by 2. So 5a minus 2b 11, 4a plus 2b equal to 22. On adding these two, 9a equal to 33. So a is equal to 33 by 9. This is 11 by 3. A we got 11 by 33 by 9, it's coming, no? Because 5a plus 4a 9, and that side is 33. So a I am getting 9a plus 3. Wait a minute, this part is 3a, okay, so this part is 3, right? So 3 means this will be 6. So this part going to be 11a. So a is coming to be equal to 3. Okay, correct. This value of a is not there. I mean a equal to 33 by 11. Okay. This is 33 by 11. So this will give us a equal to 3. So a equal to 3. Now if a equal to 3, we can get the value of b. Therefore from 1 you put a equal to 3. 5 into 3 minus 2b equal to 11. So 2b equal to 4, b equal to 2. Clear? Hope you have understood. This is just following from the definition of continuous function. Okay? But we have to learn continuity in an interval also. Before that, let me tell you continuity of some elementary functions. What are elementary functions? All of you know. Let me tell you, let me start with the polynomial function. So let us discuss continuity of elementary functions. Continuity of elementary functions. What are those elementary functions that I hope you remember by using your class 11 concept? That graph of function also you have done, isn't it? Graph of function also done for elementary functions. What you have started with for elementary functions? Let us start with the polynomial functions. Number 1 is the polynomial functions. Polynomial function. A polynomial function is of this form: fx equal to a0 x to the power n, a1 x to the power n minus 1, this way up to n. This is polynomial function of nth degree. This n must be a positive integer. Okay, n must be belonging to I plus positive integers. So let us start with polynomial function of first type. What is that type? That is which is a constant function. Okay, so let us start with that value when n is equal to 0. For a constant function, this is just for understanding. No, I need not be very systematic in proving constant function is continuous everywhere. I can state this part graphically. No one is going to ask whether it is continuous or not. Just know this as a fact. If you face continuity of constant function is of this form. If you put n equal to 0 over there, there is no existence of this term. There is only one term, fx equal to a0. That is fx equal to k. If you draw the graph of function, it is continuous everywhere. Okay? Fx equal to k, if k greater than 0, the graph will be like this. This is at a distance k unit from the origin. Clear? So this is continuity of the constant function, that is fx equal to k. This part is this function is continuous. So graph of function can be done for the first degree polynomial also. For a first degree polynomial, if you calculate limiting value equal to functional value, you will get the same thing. That's why I am not doing, isn't it? So for first degree polynomial, that is of the form fx equal to ax plus b. This graph also can be drawn anywhere in this world. Anywhere you can draw this graph. Okay, so this is continuous everywhere. Fx equal to, it is of the form y equal to ax plus b. This way, if you take quadratic polynomial, that graph also continuous. So in general, for a quadratic polynomial, graph, I am taking the easiest one. You will remember a y equal to x square, you know, or x square equal to y. This is a polynomial function. Y equal to x square, quadratic. In fact, if it is any polynomial like this, you know, y equal to, this is ax square plus bx plus c, graph is continuous everywhere. This is for a greater than 0, isn't it? For a less than 0 it will open downward. It is continuous everywhere. What about cubic polynomial? Graph of cubic polynomial also continuous everywhere. If we go for a cubic polynomial, the standard one I am taking for a cubic polynomial, the graph y equal to x cube, say we are plotting, it is also, you can draw anywhere. It is defined for all real values of x. So your conclusion will be every polynomial function is continuous everywhere, at every point on the number line. A polynomial function, to discuss continuity of trigonometric function. Continuity of trigonometric functions. Those trigonometric functions are, let us start with the sine function. Sine function, all of you know, everyone can draw the graph of sine function in this world, and the graph is continuous everywhere, isn't it? If you plot the graph of sine function, it's like this on right side, it is continuous everywhere. Even if we do it for cosine function, this is fx equal to sine x. Fx equal to cosine x, if we do, this is also continuous everywhere, isn't it? This is for this yellow one for fx equal to cos x. Problem arise with tan x, cot x, sec x, cosec x. I am not going to draw all the graphs of function. You have already done in inverse trigonometric function. Before doing that, you have revised the graph. Just let me show you for tan x. This point is x equal to pi by 2, this line, and this is x equal to minus pi by 2. The graph of the function you cannot take beyond it, okay? It is passing through origin, and this is y equal to tan x. You can draw in next part, but it is discontinuous at x equal to pi by 2. We cannot draw a graph at x equal to pi by 2. So for trigonometric function, you can divide into two categories. Sine and cosine functions. When you are discussing continuity of trigonometric functions, then we can divide into two categories, sine and cosine functions. They are continuous everywhere. Sine and cosine functions are continuous for x belongs to R. I mean at every point on the number line. What about the rest of the functions? Tan x, cot x, sec x. You are very good at plotting this graph, I know, because you have finished your inverse trigonometric function. That's why you are doing continuity. So tan, cot, sec, cosec, they are continuous. These few trigonometric functions, I am discussing elementary functions only, not composite one. I am not talking about tan x cube or tan x plus 1 by x minus. That will come automatically one after the other. Okay, tan x, cot x, sec x, cosec, they are continuous on their domain of definition only. Okay? So these functions are continuous in their domain of definitions only. Clear? So this should keep in your mind. Later on in algebra of continuous functions, we need this concept. Okay? But sine functions, suppose a question arises, prove analytically sine function is continuous. Analytical proof. Doing it for sin x. Okay, for fx equal to sin x. See, when you are writing, I'm going to tell you another way to state continuity of the function by using limits. You stated that limit, there is no confusion, there is no contradiction. This fx equal to limit extending to a plus fx must be equal to fa for continuity, isn't it? The same thing can be written as limit h tending to 0 f of a plus h equal to fa. These two are equivalent. Please don't be confused. Sometimes you will do sums based on this concept. Sometimes you do with this concept, but there is no contradiction. Why I am telling you? Because this left hand limit and right hand limit part is taken here, merged together at this point. Okay? This limit is h tending to 0 means what? Actually, it is limit h tending to 0 minus f of a plus h. Or if you don't want to use that minus sign, you just write left hand limit as a minus h by taking h as a positive quantity. A minus h will be equal to limit h tending to 0 f a plus h. This is equal to fa. Clear? So continuity you can prove this manner, you can prove this manner also. For proving sin x1, I am going to take this thing, this definition of limit. Okay? So I asked continuity of this function. I did not say continuity at a point here. At a point idea you have. So what you have to do there? You have to, for analytical proof, you will start this way. Let C belongs to domain of the function. Or C is an arbitrary point. Or because domain of function is set of real number, all of you know. What is the domain here? Let C belong, directly you write, let C belongs to R. Okay? Now, required to prove limit h tending to 0 f of c plus h equal to fc. If you can prove this, then it is done. And this will apply when you observe that the function is not stated separately for less than 0, for greater than 0. It is in general defined. So we are not planning to write that left part, right part. Directly we will find it. Let us evaluate this limit. Functional value fc equal to sin c, all of you know. Now this limit f of c plus h, this is going to be limit h tending to 0 sin of c plus h, this you write sin c cos h plus cos c sin h, isn't it? Sin a plus b formula, sin a cos b plus cos a sin b. So if I put it there, it is sin c into cos 0 is 1, cos c into 0, so the value is equal to sin c. Clear? The value is equal to sin c, and which is equal to fc. So what have you done? Therefore, this limiting value equal to the functional value. Therefore, the function is continuous at x equal to c. Clear? The function is continuous at x equal to c. It is done. And those cosec x, tan x, sec x, they are all continuous. But you have to remember their domain of definition by the same manner. If you are asked to prove continuity of tan x at x equal to pi by 2, that is not continuous. At x equal to pi by 2, the functional value, limiting value, they will not be equal. You cannot find the limit over there. Okay? But sin x, cos x, continuous everywhere. Similar is the case for cosine function. So, polynomial trigonometric function done. Now, after this, we are going to discuss for exponential functions. Continuity of exponential functions. No JEE sum today. We are just discussing the concept. We'll come with the session where those problems also to be discussed. But first you understand continuity of elementary functions. Okay, continuity of exponential here. What are those exponential functions? Fx equal to e to the power x, the best example. But it may be 3 to the power x. It may be a to the power x in general. Okay. If you plot the graph, as elementary function graphs are done already, so I'm just doing it by showing their graph, they are continuous everywhere. E to the power, 3 to the power x, whatever you take, graph is almost like this. Negative x-axis is the asymptote. Graph go on increasing this manner. This is for any exponential function a to the power x for a greater than 1. But if a less than 1, the graph will be continuing this manner. That is also continuous. For a less than 1, if you plot, the graph going to be like this. This is for a less than 1. Okay, this is decreasing function, that is increasing function. So, for continuity of this exponential function, they are continuous. We will write the comment here, continuous for all x belongs to R. Exponential functions are done. Let us go for logarithmic function. Are they continuous everywhere? Let's see. For logarithmic function, again the graph of elementary function plays a vital role. So for continuity of logarithmic functions, see y equal to log x for any base, y equal to log x. For x less than 0, it has no existence. For x equal to 0 also, it has no existence. And that is understood from the graph also. If you plot the graph here for y equal to log x, the graph going to be like this. Okay? And this point is 1. This is graph of y equal to log x base e. Okay? Y equal to log x base e, graph is like this. For x less than 0, it has no existence. So we can say that it is continuous for x greater than 0. Similarly, if base is not exponential, if base is less than 0, actually this is true for all bases where a is greater than 1. But if a is less than 1, the graph will be like this. This is y equal to log x base a graph when a is less than 1. Clear? Understand? Now, Let us do it for, so write your comment here. It is continuous for x greater than 0. Again, in its domain of definition. So logarithmic function is done. Exponential, logarithmic, trigonometric, polynomial, all these are done. There is another one that is called rational functions. Rational functions are of the form, if we take the first example, a rational function continuity of rational functions. Rational functions are of the form, say 2x plus 1 by x minus 3. I am taking this example. So for rational function also we can state that continuous in that domain of definition. It is continuous except for all x belongs to r minus 3. Because at x equal to 3 it becomes undefined. No other point is there. So rational functions are continuous everywhere. Now I am coming with two most important functions, that is continuity of modulus functions and continuity of modulo function. We have to work a lot on these two. Okay. So let us do for these two elementary functions also. Continuity of modulus function. Okay, modulus function fx equal to mod x, graphically you can state easily. Graphically you can state the graph will be like this, mod x graph. Okay, this is fx equal to mod x, and you know by shifting of origin we can draw the graph of mod x minus 1, mod, say we are drawing for mod x minus 5. Fx equal to mod x we have drawn, let us do it for fx equal to mod x minus 5. What you will do? You will just take the graph 5 unit away from origin, that is shifting of origin. This graph has a prototype at this point. Okay, only thing is that it is being shifted towards the x-axis by 5 unit. This point is 5, 0. So this is y-axis. This one your x-axis, and it is quite obvious that graphs of these functions are continuous everywhere. But suppose a question arises, show analytically, it may be a 2 mark or 3 mark question for your board paper. Show analytically this function is continuous, fx equal to mod 2x plus 1 continuous at x equal to minus half. How will you prove it? Fx equal to mod of 2x plus 1 at x equal to minus half. Graph plotting you can do. How to plot? This you shift towards left by 2 units, shrinking, expanding, all these things we will do. But this I want to see, you are getting it by the definition of continuity. I mean by analytical method. Okay. So what you have to do there when you are answering, you write fx equal to 2x plus 1 for x greater than equal to minus half, minus 2x plus 1 for x less than minus half, and equal to 0 for, isn't it? This is the, whenever mod function arises in any form, you will write this way always. So now you are going to find the left hand limit here, LHL. this is limit x tending to half minus fx. Half minus means less than. You don't put equal to over there. I have taken equal to at separate place. So x tending to half minus fx. That is limit x tending to half minus less than, oh, minus half minus, sorry. Point is minus half. You are checking at minus half. Minus half, less than minus half is this part, 2x plus 1. So you substitute there. 2 into minus half plus 1. So this is x, which is given by half plus is which part? This part. Greater than minus half, yes, sorry. So this will be limit x tending to minus half. I will be taking this part of the function 2x plus 1 equal to 0. Clear? And f of minus half is there, you can see f of minus half is also equal to 0. So you are getting 0 only. The function is continuous. Analytically, if it is required, you go by this method. Okay. Now let us do for continuity of GIF, greatest integer function. Let me plot the graph. Let me remind you the graph. If you remember, it's fine. Step function, greatest integer function, modulo function. Like Lord Krishna, it has so many names. We love this function. We maths teacher, we all maths teacher, to give you trouble in exam, we like this function a lot. Okay. So this point is 1. Next one is this, up to 2, up to the point 2. It has value equal to 1. Then up to the point 3, 3 is there. Its value is equal to 2. This you know. Up to the point 4, its value is 3, 1 less. Okay. And below it, if you draw, then it is like this. X greater than equal to minus 1 less than 0. This point is minus 1. I just remind you the graph of the function. This part is minus 3. Alright. This is your x-axis and this is y-axis. So for continuity of this function, we observe that this function is discontinuous. At which point? Function is discontinuous at 1, discontinuous at 2. Why? Why at 2 discontinuous? Because left hand limit value will be equal to this one, minus 1, 1. Right hand limit value 2 plus means it will be this one. So they are not equal. So the function fx equal to modulo x is not continuous at the integral points. Integral point means 1, 2, 3, 4, minus 1, minus 2, minus 3. At these integral points, the graph is not continuous. Clear? Analytically, if they have asked you, how to prove fx equal to mod x is not continuous. Okay, this time I am going to show you by taking x minus, okay, let us do this one, x minus modulo x will do later, let us do this one first. Analytical method. Analytically, let n be an integer. So continuity at x equal to n we want to discuss. At x equal to n, will it be continuous or not? At x equal to n. At x equal to n, the function will not be continuous. Why it will not be continuous? Because if you calculate the left hand limit, the right hand limit, the functional value, then you will observe that they are not equal. At x equal to n, what is the limiting value over there? Let us check. At x equal to n, let us check the limiting value. Board is creating some problem. I am switching to another board here. Just a minute. I will be sharing this notebook with you because that notebook was malfunctioning. Okay, just a minute. It will take few minutes only. Yes, I'll tell you. Please wait a minute. Let me settle down this new board first. Yeah. Hope this is visible to you. Let us do that sum, that fx equal to modulo s at x equal to n. You find left hand limit x tending to n minus modulo x. This n minus is smaller than, just smaller than n, so we will be taking n minus 1 over there. N is an integer, and limit x tending to n plus modulo x, this is going to be n plus means just greater than n, so it will give us n only. And fn modulo n equal to n. So they are not equal, it is not continuous. You need to check this function also, fx equal to x minus modulo x. Just check this one for continuity. Just try it once. I give you 1 minute time. Hope you have got it. X minus modulo x. Just check with my calculation. Okay, how I am doing it. For this one, at x equal to n only. We are going to check at x equal to n. So here LHL x tending to n minus, okay. See, on it limit will not work. It is n minus, it will remain n only. But here when you are taking modulo n minus, this will be n minus, this is 1. RHL will be what? Limit x tending to n plus x minus modulo x. So this will be n minus n equal to 0. They are not equal. Because on it limit will not work. N plus means it will give us n only. But on it if we put n plus means what? 2 plus. Just after 2 means 2.001. What does it give? 2 only. Here n minus means 2 minus. 2 minus means 1.9999 like that. If you take modulo, 1 will be there. 1 will be reduced over there. That's why. Okay. So this function is not continuous at x equal to 1. Clear? So with these examples you have understood continuity of function, elementary functions. At a point we have discussed, in an interval also we have discussed. Now I will be using this concept to state the algebra of elementary algebra of continuous functions. So the topic going to be in our discussion today, algebra of continuous functions. For continuous functions, suppose there are two functions, fx and gx. Let fx and gx be two continuous functions. Then their sum fx plus gx is continuous. I am talking about the domain of definition. What you have decided on it fully, on the domain of definition, it is continuous. If minus sign is there, it will be continuous. K into fx, if you multiply by a scalar k, constant, then it is continuous. Fx into gx, that is also continuous. Problem is there for fx by gx. Fx by gx is also continuous if gx not equal to 0. Clear? If gx not equal to 0, it is definitely continuous, fx by gx also. So with the idea of elementary function and these properties you have learned, if someone is asking you discuss continuity of the following function, they are not telling about any interval. Let me write the sum. We are going to discuss continuity of this kind of function. Say continuity of the function. No interval given. It means over the whole number line that fx equal to 3x square plus 4 x greater than 1, 7 for x less than 1, and 9x minus 2, sorry, x equal to 1, this part is x equal to 1, x equal to 1, and 9x minus 2 for x less than 1. They haven't mentioned that check continuity at x equal to 1. Their continuity they have asked you to discuss means you have to talk about the whole number line. Clear? So this will be continuous if, so your answer will be like this. The function being a polynomial one or being a polynomial function. See, this is a quadratic polynomial, you can identify. This one is a constant polynomial, you can identify. This one is a first degree polynomial. The function being a polynomial function, being a polynomial one everywhere, I mean greater than 1, equal to 1, less than 1. Everywhere it is polynomial function. It is continuous for all values of x, but continuity at x equal to 1 is doubtful. Why it is doubtful? Continuity at x equal to 1 is doubtful. Why? Because x equal to 1, the nature of the function going to be changed, isn't it? Quadratic to constant, constant to first degree, like that. Okay? So we check continuity at x equal to 1. If it is continuous at x equal to 1, we will say that it is continuous everywhere. Got the logic? So for continuity at x equal to 1, for continuity at x equal to 1, left hand limit at x equal to 1 will be what? X tending to 1 minus fx. So it is 9x minus 2. 9 into 1 minus 2, that is 7. Okay? RHL at x equal to 1, 1 plus fx, x tending to 1, what? There will be 3x square plus 4. So this is equal to 7, isn't it? And f1 is what? That also you check at x equal to 1, the value is 7. So you got all these three equal. Left hand limit, right hand limit, functional value equal. So your conclusion is the function is continuous at x equal to 1. It is continuous everywhere. Now we are taking another kind of problem. Say if x equal to, given like x plus 1 by so this is the ratio between two polynomial functions. Numerator is a polynomial function which is defined everywhere. Denominator is a polynomial function, defined and continuous everywhere, there is no doubt about it, but it is in denominator. Function being polynomial, continuous over there and there, but here denominator, if this one vanishes, it will not be continuous. The function is discontinuous when x square minus 4x plus 3 equal to 0, x minus 1, x minus 3 0. So your answer will be, it is continuous everywhere or continuous for x belongs to R minus these 2 points, isn't it? This way you need to answer. Let us take one example from the textbook, then you try, and next Tuesday I am coming back with few more problems on continuity. Okay, types of discontinuity also will be discussing. If they have asked you this kind of function, textbook type of functions, I told you, it is a x cube sine 1 by x for x not equal to 0, 0 for x equal to 0. Okay. So is this function continuous everywhere? How do you write the answer here? Today's session, this is the last problem on continuity. Okay, you will try, you will write your doubts here. I will solve, and then Tuesday we will be sitting again from 6:30 to discuss more on continuity sums. So here how to answer here? Answer. For continuity, put the statement. Today is I am discussing only how to answer both type of questions, no? And discussing with elementary idea. For continuity at x equal to 0, limit x tending to 0, fx equal to f0 must hold. This one must hold. Okay? Here fx x cube sine 1 by x. Here if you put 0, sine 1 by 0, you cannot decide. But one thing clear, sine 1 by 0 is a finite quantity. It is lying between -1 and +1. So you will be writing here by putting 0 into a finite quantity, the way you used to do in limit problem in class 11. Same manner. A finite quantity lying between -1 and +1. This is equal to 0. So the function is continuous at x equal to 0. Why? Because f0 already given. What is f0 here? That is 0 only. Okay? Hope you have understood the elementary idea of continuity of functions. So what you will do? You may be going for JEE, Main, Advanced, ISI, CMI, whatever. Your first book is your textbook. Maybe NCERT book. Those who are in different board, they may be doing from Saha and Saha, all those books. Do. From any elementary book, you have a good concept first. I will be sharing a material also just after finishing your textbook. You will be seeing that. Okay. See you again on Tuesday.